He's one up on Chu. I said he draws the line. He's one up on Chu.
Hello, good afternoon. Welcome to ECE210 class. Today I will talk about new chapter. I will start a new chapter from your book, chapter 7. But before I go there and start, I'd like to review very quickly what I told you yesterday. We talked about if we have a signal ft, and if the signal is periodic, then we can use Fourier Series and calculate Fm, right? And then I introduced a new concept called average power, the average for the signal. And just take away the word average for now, because from now on, when I talk about, when I write P, I mean P average. And Pf was defined as integral over period, normalized to period, ft absolute value squared dt. So this was the power stored in the signal in one period. And then we learned that we can also use Parseval's theory because this calculation sometimes is easy in time domain, but some other times it's not easy, it's difficult. So Parseval actually played with this calculation, manipulated this mathematically to come up with a new formula for PF calculation. Which was this. So what actually Parseval says, it says that if it is difficult for you to integrate your signal in one period, you can go to Fourier series and then sum them. This is discrete summation, right? All the components from minus infinity to plus infinity, and he guarantees that this PF is same as this PF. So it depends on you. You have to pick and choose. And we learned that there are sometimes easy go with this, and some other times easier to pick this one. And after this, I talked about total harmonic distortion. Forgive me that I guess I used this, but I meant this. Please correct in your notes if it's TDH. So THT was defined to be, anyone remembers?
1/2 magnitude of Cn.
Okay, Cn squared from
N equals
2 to infinity, and there is a summation actually in here. I have to remove it. Yeah, it's just going to be C1, right? So what it says what it's trying to say is how much energy is stored in second, third, fourth, fifth harmonics comparing with the fundamental signal. So we like this number to be big or small? Small, right? Okay. That's pretty much what I covered yesterday. And
why don't you consider DC term?
what's that?
Why don't you consider the DC term?
Yeah, the DC term is not considered in this calculation.
Why?
I don't really know why, because I know why. Because they can't filter it out by an easy capacitor, a simple capacitor. So if you have a DC component in your signal, let's say I have this signal, okay? And this is a pure sine, okay? If this guy is distorted by a DC component, instead of being in here, it's gonna shift it up, right? It's gonna be like this. That's what DC does to a signal, right? But if you simply pass it through a capacitor, the capacitor, they call it decoupling capacitor. It's gonna remove that DC and bring it back. It's a DC level shifter, right? So that's why we are not very worried about DC component because we can remove it simply. But the other harmonics, second, third, fourth, fifth, very difficult. You cannot easily remove them. You need a very good filter, and to design a filter that can heal all of those harmonics is not very easy. Okay. So if I wanted to add those harmonics, can you guess what could be my shape? Let's say, I forget about 2 and 3, go very, very high. Let's say harmonic number 6 with very small amplitude. It would be like this. My final shape was like this. See? Instead of having a pure sine, I will ended up having such a thing. And you will see this when you do measurement with oscilloscope so much. Okay? And sometimes you can remove it by adding a few AC decoupling. It's a button in the oscilloscope. You can press it and make it pure. But sometimes you cannot. When you press that button, don't forget you're removing these components. That's what's happening here. Any question? If I'm fast, please tell me that I can slow down. So, again, up to now, we just talked about periodic signals. By periodic, we mean that if you just observe your signal at one specific interval, which is called period, and we use capital P to show it, then you know what's going to happen to the end of the axis, right? You're just going to repeat it. So let's start this. Not so much information in the rest, right? All the information is in here. I tell you this, you know what's going to happen next, 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 next. You don't need me to tell you what's in here, because you know it already. Just repeat it. Right? But what happens if this t, let's say this guy, the distance between these two guys is t, right? Right? That's what period actually is. What happens if this t starts going to infinity? Big number. It's an infinity, but big. Okay, let's make it right. Let's say the second guy is going to repeat here. Oh. This is a new t. T2. Bigger than, if we call this T1, T1. So if I keep increasing t, this guy moves away, right? And away and away and away. And eventually, if, for instance, this is the window of interest that I'm looking at, I won't see any other signal. rather than the basic or fundamental signal. I mean, this one, just this one, right? Do you think this signal, if I just show you this, do you think this signal is periodic? No. Why? Because there is no repetition of the signal, right? And you don't know what's happening after this. And you know, when you do any measurement, when you do any simulation, there is always a time window. How is time window? You have to set it. You cannot ask your measurement tool to measure for days, or weeks, or there is always a limit. You can ask it to collect data in, let's say, 5 hours, for instance. Depends on your application, 5 minutes. Okay. If in that 5 minutes this shape repeats itself, that system, that oscilloscope is going to decide that you have a periodic signal. If not, it's going to decide that your signal is not periodic, right? And that person, let's forget about oscilloscope, because the oscilloscope itself always assumes there is a periodicity in your signal. But the person who measures, after 5 minutes, reach to this point that, hey, it is not going to repeat itself, I give up. So this signal is not periodic for that person, but if another person comes and wants to do measurement for 5 hours, maybe he observes or she observes something with a very long period, right? Or maybe she cannot observe anything because the period is really, really large. So we call this kind of signals aperiodic, and this is a very relative word. When you say it's aperiodic, it depends on observation window. Okay. So we learn periodics, and now we learn aperiodic signals, which there is no repetition. We assume that there is no repetition of this shape, so they are aperiodic. Any question here? So now you may ask yourself, okay, Fourier series was only applicable to periodic signals. Up to now you learned this, but is there any way that we can apply Fourier series or something else similar to Fourier series to aperiodic signals? So what I'm gonna start writing here is mostly math. And I have to do some mathematical manipulation. But what is the whole purpose behind? I am looking for a way to show a periodic signal using Fourier coefficients. The whole thing I'm going to do. I'm going to try to see that if I can somehow find a way to show this signal using Fourier coefficients. So let's start from ft equal summation goes from minus infinity to plus infinity fn ej and omega naught t. This is well known, right? And we know fn was 1 over t, integral over period t, ft e minus j and omega naught t. Right? We know this too. So now, as we know this omega 0 is 2 pi over t, so I can replace this with that, and I get t is 2 pi over omega 0. And the integration I can always pick like this. It's up to us. We can use this. So t is going to be 2 pi over omega 0. So half of t is going to be minus pi over omega 0 to pi over. Right. Ft E minus j n omega naught et. I haven't done anything up to now. I just replaced t with this, right? So now, can I change this equation? Just take it here. Can I change this equation and just move this guy here and this guy here? This is possible, right? We can do that. It's omega 0 goes here. 2 pi comes here. Fn equal minus pi over omega naught, pi over omega naught ft e minus j n omega naught t. So, I asked you a question. What was Fn? What kind of values? I mean, is Fn a discrete function or is it a continuous function? Let me ask this question. Discrete or continuous? Fn was discrete, right? It was one. I mean by discrete, I mean that this f, you can look at it like this, right? It was function of n omega zeros. Only at certain discrete n's, Fn has value. Between them, the value was 0, right? We knew that. This was Fn, this was n omega 0. So at omega 0, 2 omega 0, 3 omega 0. So at omega 0, it had a value, usually the maximum, and then 2, and then 3. Between them, no value, 0. Right? That's why it was discrete. Fn was discrete. So, you learn function, a concept named function, right? So can I look at Fn as a function of n omega 0? Yes. That's quite possible, right? Fn is a function of n omega 0. So let me do this. Instead of just leaving it like Fn, from now on I like to write it this way. Fn as a function of n omega 0. And this coefficient, I will keep it here. And this integral, I won't touch it. So now I'm going to do one more step, and that is related to what I told you in here. When the period goes to infinity or big number, if t goes if t moves toward a very big number, omega 0 is going to move toward a very small number, right? So can I use this notation for now? Omega 0 goes to 0 in here and here to see what happens, right? I'm trying to find out about this periodic signal, right? So that's why I need to use the limit. In the limit, when omega 0 goes to 0, I can replace n omega 0 with omega, and fn with a function called f omega, and the whole omega 0 over 2 pi, I will save it for future. Okay, let's keep it. Okay, so instead of writing n omega 0, because omega 0 is very small, this quantity looks like a continuous quantity. Omega is no longer discrete. It looks like a, okay, these two are moving toward each other. The distance is very small. Instead of using omega 0 and 2 omega 0, I'm using omega for now, which omega can have a very continuous range. Everything between can be omega, can be included. So I'm replacing n omega 0 with omega. And pi over omega 0, if omega 0 goes to 0, it's going to move toward minus infinity. This to plus infinity. Ft is not going to change, but this guy again n omega 0 will be omega. you're done. That's what we were looking for. So we have it. But big step was going from here to here, and I hope that you understand what's happening here. We don't have n anymore because the omega 0 is very small, so we have a continuous range. Instead of having omega 0 at 2 omega 0, right? It is 2 yet, but omega 0 is very small that we can replace it with only omega. It's a continuous version of that. So let's keep this. So omega 0 over 2 pi f omega is this integral, and I'm going to take that and come back here, and I write it back, I write it down in here, 2 pi, okay, omega 0 over 2 pi, f omega is minus infinity to plus infinity, right? Ft e minus j omega t dt. And Ft, we still remember, Ft was the summation, right, from n negative to n positive, f n e j n omega 0 t. We had this right in the beginning. So you can see this is no longer applicable because Fn is no longer a series. Fn is going to be f omega, right? So if we use this for, instead of Fn, if I use this guy here, what I'm going to get is forgive me for using series while I don't have n anymore in here. Yeah, just I keep this as an interim step, but this is not mathematically correct. We cannot do this unless we replace this, because omega 0 is very small, again, same argument. I can replace this summation with an integral. And remove this 1 over 2 pi out. Keep the omega as in d omega. And it's going to be f omega e minus j omega t. And omega 0, we have to replace it with omega because omega 0 is very small. So haven't done much. This omega is in here.
I think f of t is fn e to the power of plus j and omega naught t.
Oh yeah. Thank you.
So you're in your series. Yeah, that should be plus.
Thank you. We are done. I know the math maybe bothers you, but if you just look at it, there are some assumptions in here, and we don't really need to know how to calculate these things back. It's just the concept is important. The concept is, I'm gonna summarize this somewhere here, maybe after you finish. I can erase that part and summarize it. You need to just memorize or learn and understand two identities from now on, which are as important as Fourier series. And how to go to Fourier series, how to calculate the coefficients. So what we learned was Ft can be written as 1 over 2 pi integral from minus infinity to plus infinity f omega e j omega t d omega. And then f omega can be calculated as integral from minus infinity to plus infinity f t e minus j omega t dt. This pair actually is known as Fourier Transform. and inverse, or vice versa. This is inverse actually. Inverse Fourier transform, and this is Fourier transform. I know this 1 over 2 pi is a little bit confusing because in series you have this 1 over 2 pi in here as 1 over t. That's the only confusing part when you go from series to integral. Otherwise, what you actually did was you replaced summation with integral in here. Before we had a summation. Any question here? Do you understand what's happening here? I'm going to explain it a little bit more. But more you spend time with these two, this pair actually, you will understand the physics behind and what's happening. But I try to transfer some. One thing that you learn here is if your signal is not periodic, let me narrate it this way. If you have a periodic signal, if you have a periodic signal in time domain, I call it periodic P for now. Maybe periodic. If you go to Fourier series, you have to look for a discrete representation. It won't have all the components. This is, if I call this omega, and this is your f omega or fn omega 0. Let's say fn omega. Okay, this is fn omega. I call it omega. I use this omega here, and as you can see, it cannot have a continuous range of frequencies. Okay, so if you use this, anyone knows which device, which instrument can do this for us if we actually plug in a signal like this as an input, and then it provides us with the spectrum? What's that? There is a device, there is an instrument. What? Op-amp? More complicated than one op-amp. It may have many op-amps inside. It's a big device and expensive. It's a spectrum analyzer.
Oh, that was my second guess.
It was? Yes. Yeah, a spectrum analyzer, I don't know if you guys work with it or not, but you will in future. What it does, if you take the signal, this is a device, it has an input, right? So if you take the signal as an input, and then it will show you at the screen this signal. Exact same thing, you will see it. They are discrete at certain frequencies. And those certain frequencies are dictated by the period of the signal. Omega 0, 2 omega 0, 3 omega 0, 4, minus. I mean, there is no minus in spectrum analyzer. It shows you from here to up. It won't show you below that. That's another way. What's that question?
Why does that quantum equation kind of look like the Laplace transform?
Yeah. It's Laplace. Fd minus Sd dt. That's Laplace. Laplace is this is a member of Laplace family. If you set S at j omega, then Fourier is Laplace. It's a good observation. Or maybe negative.
No, plus
But then
sigma.
wouldn't the negative
Oh yeah,
infinity
that's,
be
I
zero?
mean, it has plus. Just, what's that?
Wouldn't the negative infinity have to be 0 for it to be Laplace?
Should be one.
0 to the positive.
Yeah, I mean, Probably you're right. I don't remember, I don't recall if Laplace was from 0 or from minus to plus. But if you think it was from 0 for Laplace, yeah. But these two are from same kind of, there are many different transforms. Laplace is one. This is another one, Fourier. But why we like this better? Because it works directly with frequency. But S, as Aditya was mentioning, can be a complex number. So it's general, right? It can be sigma plus j omega. But for our discussion, we don't have any source which has sigma. No, your source is a sinus, a cosine. But if you have a source which is damping by time, then you need to use sigma. Because you have to model the damping. But in real world, your source are not damping source. You have a power source which is providing, fortunately, very pure sinusoid for you. So you don't have the sigma anymore. But if you have a source which is damping, you cannot use these equations because your source is dying, right? You have to model it using sigma. That sigma is gonna, if you multiply by t, a negative sign, e minus alpha t, it will die over time, right? That's why we need to go to complex.
So the Laplace transform and the Fourier transform are part of the same family. Is there a differential equation like part of it from both, part of itself?
Can you repeat your question?
If the Fourier transform is in the same family as the Laplace transform, then is there a differential equation that solves for those two?
Yeah. If differential equation to solve to reach to Laplace. Actually, Laplace is only a transformation. I don't think there is any differential equation assigned to Laplace, right? It's only a transformation. I don't have so much time, but I can just quickly show you that in future you will learn this. If you have a circuit like this, if it has a capacitor here, and your source, it is pure sinus, you instead, in a steady state, instead of solving this in time domain, is so much of trouble to solve this because it's this guy, the current here, is C dV over dt. This guy is simple. V over R, excuse me. So if you want to calculate, if you use Kirchhoff's law to calculate, if you know the voltage here, the question always is what is the current, right? To do this, you should write differential equations to solve this, right? I don't know if you did this or not in any course. You did? Okay. This is very difficult to do it because you have to solve differential equations. But there is another solution that you're learning today. You can actually, if this is a pure sinusoidal source, you can move the circuit to another domain, okay? Transform it. And instead of doing this, in the transform, this C dV to dt is going to be Cj omega, Cj omega V.
They've already learned this.
Yeah, V over J sigma. And you treat this as an impedance. So you don't have any differentiation anymore. It's very simple. You divide this, you say voltage in Fourier, okay, divided by R. R won't change if it stay as it is, plus 1 over J C omega. This is going to be my current in Fourier domain. See how beautiful it is? It's so simple. You don't have any differentiation here. So after you calculate your I versus frequency, you do this guy to go back to time and report that in time domain.
They've already learned this.
They learned this? Okay. So you can, okay, now the question is, where is the Laplace coming into the picture? Now assume that your source is not a pure sinus, and your source is E minus alpha t, E minus j omega t. You cannot use Laplace. So you cannot use Fourier. Because you have a time-dependent source, which is not just sinus, right? It's decaying. So what you have to do is you use S equal alpha plus j omega. And instead of j omega, everything will be S. And then after you calculated everything, you replace S with whatever number is this. And of course, you have to do inversion in Laplace. It's almost the same equation. And then replace S with this. That's what you need. So, thank you. Any question? I know it's a new topic and it opens many doors for doubt. It's good. You can think about it, that where you can apply these equations. There are many, many, many applications for Fourier. Many. And okay, let me come back here and just shed some light on this new concept, new transformation. As you could see, if we had a periodic signal, if we use a spectrum analyzer, or if we calculate it, we're going to get discrete representation in frequency domain or Fourier domain. Now, what will happen if these two start moving away? Okay. So let me ask you this question. What is the distance between these two? Omega 0, right? So now if I increase T, I'm decreasing omega 0. What happens, these two arrows are going to come closer and closer, right? Instead of this distance, let me draw them equal. Okay. This distance is going to be much smaller, much smaller. And so the distance keeps decreasing, decreasing, decreasing. And at one point, when this guy is very far away, my spectrum analyzer, you know, any device works at discrete, in a discrete way. There is no continuous way in the real world. Everything is discrete. So, but to